Good morning, ladies and gentlemen. On to momentum review. Momentum is inertia in motion.
Yep, and it's a simple thing. It's mass times velocity, and the symbol for it is P.
Boom. How can we make this equation look like this equation? So how can we make this look like this?
Yeah.
Well, what's our equation for acceleration?
Acceleration is the rate of change of velocity.
E over t. Now we've got mass times velocity over t. Let's just get rid of that t and put it over here. And what does that get us? It gets us our impulse momentum theorem. So our impulse momentum theorem, impulse changes momentum.
Yeah.
And what we just did was we had mass times velocity, and we took that mvt, and we divided that, we multiplied that t, put it over here, and that's how we get that force.
That's the change in momentum. And this is a very important idea, and like we reviewed with the work energy theorem, this is also a fundamental idea.
I'm just gonna write that over here real quick for us. Delta T equals delta. Okay, I feel like we're gonna use that coming up here. Okay, our units, kilograms, meters per second.
Units of mass are kilograms, units of velocity are meters per second.
And here we have, so we've got impulse is the force times the time interval, and so units for force are newtons, newtons for time is seconds.
That's right.
What is a newton? A newton is a kilogram meter per second squared.
Yep.
Right? Is it okay? And of course, whenever we're talking about the change of momentum, we always do the final minus the initial.
And anytime something changes in physics, is always a final minus the initial. That's why you can keep the sign of the answer straight.
Uh-oh. Okay, so here we are. Let's string them all together. You've seen this before. You have experience with this. And we can manipulate, we can solve for, whatever we need to solve for. Maybe it's force and final velocity. Maybe we've got these two. Maybe we've got, I don't know, these two. Whatever.
And here's the thing. Can you speak algebra? This is our definition of impulse. It's force exerted over a time interval. Well, what does impulse do? Changes momentum. Well, when momentum changes, how does that work? Well, it's a final minus the original. Well, when the momentum changes, what changes? It's not the mass, it's the velocity. Well, when the velocity changes, that's just a final minus the original. So what this is, the reason, it looks pretty intimidating, but all it is just they're all equal, and depending on what you've got, you select what's appropriate.
Boom. Okay. A system, a defined set of objects and the energy associated with them.
Yeah, system is a device that science uses to simplify the universe. You focus on a particular thing and it allows you to understand, because the universe is complicated.
Simplification. Internal forces exerted by the objects on each other. Newton's third law, say they sum to zero.
Yep.
Right. Okay. External forces come from outside of the system. In an isolated system, external forces sum to zero. We just
Yep.
we ignore those suckers. Okay. Conservation of linear momentum. Okay, so the total momentum of a closed isolated system is constant.
So absolutely. So that means that no forces from the outside are going in and no forces from the inside are coming out. So that means that momentum doesn't change.
And this is a really important concept. There are two general categories of conservation of momentum examples. We have explosions and we have collisions.
Remember Mr. Boykin on the bowling ball. I was on the skateboard with a bowling ball. That's an explosion.
Okay, so for all momentum situations, that we have an initial momentum, some event occurs, and we have a final momentum.
Yeah.
And let's go ahead and take a look at that first type of event, and it's an explosion, where our total momentum is equal to zero, and we might have something like zero equals, initial momentum plus final momentum. We did some subtraction. This is the bowling ball, right? And the skateboard.
Bowling ball and the skateboard could be a rocket ship in outer space that fires gases off in one direction.
Or they tend to do like the gun problems, right?
Yes, that's true.
So any of those sorts of things. Oh, and there was one in the homework that was like, there's two people in a canoe. One of them gets out. Or something like that. Okay. And here we are.
Wait a minute, we missed.
Oh, there we are. Sorry. Okay, so collisions, so explosions, and now we have collisions where the total momentum does not equal 0. Rather, you have to figure out what's going on here.
Yeah.
And so what does that look like? Things will either, two objects will collide and bounce off or stick together.
Yep.
What is the difference between momentum and kinetic energy? Okay. Now, two ways of looking at this. So the first is that we know that kinetic energy is 1/2 mv squared.
Yep.
And we know that momentum is equal to mass times velocity, right?
So just looking at the equations, you can see the equations are different, but really the idea goes back to what you have at the top with what changes momentum with what changes energy. So for the top, you could work equals force times displacement equals a change in energy.
Yeah, okay. Which is, kinetic energy and again, all that.
And so we talked about this yesterday. What's the difference between these things? Impulse, momentum changes over a time interval.
Yeah, so the
Energy, work is done through a displacement. Force causes the change in momentum, the change in energy, but it's a different way of looking at them. And this is what helps you recognize just what you're looking at when you encounter a problem.
Yeah, what kind of problem are we dealing with here?
Yeah.
Okay. A collision occurs at a point in time before and after. These are the questions you need to ask yourself. Pause for a second. We have explosions. Now we're talking about collisions, two types of collisions, and what stays the same always, no matter what kind of collision you have.
Yeah.
And then what changes.
Yeah.
And so linear momentum is always conserved no matter what type of collision you have.
That's right.
But let's talk about the energy. So the total energy is always conserved. It doesn't disappear, but we do see some different things happening with our different collisions.
The problem is there's so many different kinds of energy.
Yeah, there is.
There's heat, there's light, there's sound, there's a bunch of things.
All this stuff, thermal heat. So what about mechanical energy? That's what we're going to be focusing on.
That's the good question.
Okay? And when we say mechanical energy, we're talking about motion. Since motion is involved, kinetic energy is the mechanical energy of interest. So what does this mean? So before we said that the conservation of energy is always conserved, of momentum is always conserved.
Yeah.
But energy is something that changes depending on the type of collision we have. So if we have an elastic collision, the kinetic energy is going to be the same before and after.
Yep.
Now, think back to when we were playing with the red and blue cars on the track,
Yeah.
right? And I think there was a magnet in between,
Yep.
right? And that made it an elastic collision.
So when they had a collision, they didn't actually touch. It was
Yeah.
the magnetic fields interacted.
Yeah. So what we have is a car sitting still and a car moving, right?
Yeah.
And it ran into it and they both moved away.
Right.
Right. But the beautiful thing here is that when we did our measurements, kinetic energy was the same. We're going to call it the same before and after. No
Yeah.
kinetic energy was lost.
Yeah. Magnetic fields are conservative forces.
Yes. Oh, and we just talked about that.
Yeah.
Okay. If we have this is an example of an elastic collision. A 2 kilogram ball is rolling at 4 meters per second and strikes a stationary 2 kilogram ball. The original ball is stopped. Okay. How fast does the second ball roll away?
Yeah.
You could do the math for this, but based off what we said, it's got to be 4 meters per second.
Well, the momentum before is equal to momentum afterwards. The momentum before is going to be 2 kilograms times 4 meters per second. That's going to be 8 kilograms meters per second. And the first ball has 0 momentum. Afterwards, the second ball has 0 momentum. Afterwards, the first ball stops, and the second ball goes away with 8 kilograms meters per second. Since they've got the same mass, they'll have the same velocity.
Do I need to draw that, or I think we're good?
I think we're all right.
Okay. Oh, you want to do that? There we are. Okay. Now we asked this question in your notes. See if you can find it. You probably already did the work.
Yeah.
Okay. If kinetic energy is lost in other forms of energy, we call this an inelastic collision. But keep in mind, linear momentum is always conserved. what did this look like with our lab that we did with the red and blue car?
It's when we had the Velcro.
Yeah, so they ran into each other, and then one of them was going a certain speed. When they ran into each other, they stuck together. That's one characteristic there. But more importantly, they moved off together slower.
Yep.
Okay, so that's what we mean when we say kinetic energy is lost to other forms of energy. It's not lost forever.
Yep.
Okay, so that is inelastic. Okay, so
This is something completely different.
new concept here, new topic. How could we predict where the balance point would be if we hang a 0.2 kilogram ball at 0.15 meters and a 0.5 kilogram ball at...
So here we've got a meter stick with 200 grams at 15 centimeters and half a kilogram at that, and it's obviously not balanced in the center. So how could you find the balance point?
So I'm not going to move that way. It won't work. So I'm going to go ahead and move this way. Whoa, this is hard to hold.
Now don't try to balance it on your finger. Try to hold it like,
There we go.
So it's going to be somewhere around 59 or 60.
Yeah, okay, so 59 or 60 we say. I'm just going to put that
So
back
it doesn't
there,
balance in the middle, it balances somewhere around here. Why is that? Well, this one is heavier and this one is lighter. So if they were both the same distance, remember when we talked about torques,
and they were the same masses. If they were the same distance, same masses, they would balance.
Yeah.
Okay, but
they
the
are
levers need to be a little bit different there. Okay.
So,
where's my mouse? There it is, okay? So this balance point is called the center of mass, okay?
center of mass.
That's our center of mass. In a one-dimensional horizontal system of two bodies, which we just saw.
Yeah.
Here's our equation. I'm going to go ahead and write this equation up on the board. You might be like, oh yeah, I sort of remember this equation. So the center of mass is going to be equal to the mass 1.
Where's the first mass?
Okay, plus the mass 2, x2, over m1 plus m2.
So let's see, mass 1 is, what was it?
0.2.
0.2, and it was at 15 centimeters.
And I want to have it in meters, right?
No, it doesn't matter. 15 centimeters work. 15 centimeters plus the other one was 0.5 kilograms at 80 centimeters divided by 0.2 plus 0.5.
Okay, so here we go. Should we do this with them or can they do it?
Well, you do it, we'll do it too.
All right, so we'll do.
We better get
0.2
something around
times-
60.
Yeah, 15. Okay, plus 0.5 times 80. Wrong way. Delete. Okay, divided by 0.7, and I get 60.1.
Yep. So we could physically, empirically try to figure it out by holding it up right about there and get a balance. Or we could use the equation.
And you can't always hold it up, so.
Yeah.
Okay, so notice that this is almost like a weighted average, right?
Yeah.
Okay.
It would be an average, but we're talking about how much mass it is.
Okay, what would happen to the center of mass if one or both were moving? Okay, so what if I, were to bring this in, or what if I was to move that out or move this in? What would happen to the center of mass then?
Well, it would not be at 60 anymore.
No, it would change, right? And so we have an equation that reflects that concept, and it's just right here.
And all we've done is add delta x.
Yeah, because we can move, if you move this, if you change this, this changes respectively.
Yeah.
Okay. All right, so
We need a diagram for this.
we do. Okay, so not like a new concept here. This is review for everything, but let's talk about a different situation. Okay. It says if the 0.2 kilogram ball, okay, is moving at
Positive 2 meters per second.
Okay, and the 0.5 kilogram ball, okay, is moving at -1
Yeah.
meter per second. what is the velocity center of mass?
The velocity of the center of mass is going to be 0.2. Yeah,
There's our equation for it.
let's do that.
Okay. So velocity center of mass is, I'm gonna go ahead and I'm gonna write this here first, so that way you
Now,
guys.
you're going to run out of room.
I am, yeah. You know what? Yeah, you're right, because I gotta do the other stuff too.
Yeah.
Okay, so we're gonna do
Just-
M1V1, so 0.2 kilograms times
That's what
2
we're doing.
meters per second. Okay, plus 0.5 kilograms times -1 meters per second. Okay, divided by, and then I just add them up together. That's gonna be
0.2 plus 0.5.
0.7, right?
Yeah. Uh-huh.
Okay, so this is gonna be 4 kilograms meters per second, right?
0.2 times 2 is going to be 0.4.
Oh shoot, that's a 0.2. Make sure you can read your writing, ladies and gentlemen.
Yeah.
Okay, and then 0.5 times -1 is just negative 0.5 kilograms meters per second. Okay, so this is just the total momentum up top.
Well,
That's what I'm seeing there. Huh?
yeah, we'll get to, yeah.
Okay.
Uh-huh.
So then 0.4 minus 0.5.
It's negative 0.1
Is it negative 0.1?
divided by 0.7.
Is 0.5. Negative 0.1. Okay, divided by 0.7. We get negative point. Oh, that was my new student. Negative 0.14 meters per second here. Okay.
Okay, so the
Elegant.
velocity of the center of mass is to the left. Now, I got a bigger velocity to the right and a smaller velocity to the left, but we have a much larger mass and a much smaller mass. So that's the velocity of center of mass.
It's not moving very fast. Okay.
And now, what do you notice? You, Miss Moore, you noticed.
Yeah, as I was doing that, I realized that the top, it's just, the numerator is just the total momentum of the system, right? So I'm just
There's a
adding up.
momentum of one plus the momentum
Yeah.
of the other one divided by their total mass.
Yeah, so if you're like, wow, this is a lot of letters to remember, it's just total momentum over the total mass,
Yep.
okay? All right, so what next here? What does the law of conservation of momentum say about the velocity of the center of mass? What does it say about the velocity of the center of mass? Okay, so we know that this is our conservation of momentum, and if this is our mass 1 plus mass 2, and this is our velocity center of mass, and this is not changing.
Yeah, because the total momentum doesn't change. The mass isn't going to change. What does that say about the velocity of the center of mass?
It doesn't change.
It can't.
It can't change. And I don't know if you guys remember this. This stuck out to me when Boyk and I were showing you guys the two ball simulation
Yeah.
a while ago, and we had the two balls coming towards each other, and then they hit off each other, and they kind of went off the screen. Now there was a little dot on there that showed the velocity of center of mass, and no matter what happened, it didn't change.
It didn't change.
It didn't change.
That's right.
And so this is a really important concept here.
Very useful concept.
It's
too.
useful, yes.
Yeah.
Okay, so the velocity of the center of mass of a system cannot be changed by interaction within the system, any collision or explosion.
Yep.
So, what would be the velocities after the balls after they collided?
Well, what we're asking for is two variables here.
Yeah.
We know that the masses aren't going to change, but the velocities are.
Yeah, I want to know the final velocities of both these. I'm not going to draw arrows on there. 'cause
And we don't know what direction, we don't know anything. So,
How do we do this? Okay, so the first step is to find the velocity center of mass, which we've already done. The total momentum over the total mass. What is next? It says subtract the velocity center of mass from each of the velocities. So I think that means I'm going to come back up here. I'm just going to say positive 2 meters per second right here, and this is negative 1 meters per second.
yeah, minus 0.14.
Minus 0.14. Minus 0.14. Okay, that's gonna give me
2 minus 0.14
Is that gonna be
is
point?
1.86.
I think that's right.
1.86.
Okay,
And this should be 0.86.
0.86.
Well, negative
Negative
minus a negative is the same as,
I get one.
you get a 1.14.
Yeah, 1.14. Yeah, I was like, wait, hold on. Negative 1.14 meters per second. Okay, what's next?
So we have just subtracted the velocity of the center of mass from the velocity of the balls originally, Now we have to change the sign of each. So this over here becomes negative, and that becomes positive.
Okay. So now we just have to add the velocity center of mass back to each of the original ones.
So that's negative 1.86.
Should I write down here?
No, you were not adding it to the. We were adding it to what you have right there. So that's going to be negative 1.86 plus
0.14.
0.14. And this is plus negative 1.14. See,
should this be a negative here? Sorry.
See what we're doing? We're adding the velocity of the center of mass. So you're adding a negative 0.14.
Over here, right? Yep.
Yeah.
And then over here, negative 0.14.
Which is the same as subtracting.
Yeah. Okay. All right. So we have negative 1.86. Okay, plus a negative 0.14, and I get negative 2.
So draw a ball
Okay.
with 0.2 kilograms and a velocity of negative 2 meters per second. Okay, now what's the half a kilogram going to be doing?
Okay, so we've got 1.14 plus a negative 0.14, and I get 1.
It's going to be going 1 meter per second positive.
In the positive direction, 0.5 kilograms.
So we have just solved for 2 variables. So the 0.2 kilogram ball is going to be going back in the other direction at the same velocity, negative. And the half a kilogram is going to be going in its opposite direction at 1 meter per second.
Now, Boykin, you're sure that we used this original one? We don't add it back to the original velocity there?
Subtract the velocity of the center mass from each, change the signs of each, and add the v. No, we did it right.
We did it right? Okay.
Yeah.
All right. So, there's a way you can check this. I can't remember. We'll skip that for now.
Let's just go on.
Yeah, I think this is our last slide here. Okay. So that's how we find our. So this is how we solve an equation for 2 unknowns right here.
Yeah.
And it's really simple. Just gotta follow the steps. Bada boom, bada bang. And there it is.
But the big idea is that the velocity of the center of mass does not change.
Does not. Okay.
All right.
And we have a few questions for you guys to do for the AP test. They are right above on the homework.
Okay.